Hello there, and welcome to the Scientist Sleepy. Tonight, we embark on a gentle exploration, a calm lecture, into one of the most profound mysteries of existence. What lies before the Big Bang? It's a question that touches upon the very fabric of reality, a fascinating phenomenon that challenges our most fundamental assumptions about time, space, and beginnings. Prepare for an investigation into extraordinary, and at times, surprising, scientific concepts that might just offer a new perspective on our place in the grand cosmic tapestry. Let us now begin to drift. The universe existed before the Big Bang. Our current, most widely accepted model of the universe is the Big Bang theory. It describes how our universe began in an extremely hot, dense state and has been expanding and cooling ever since. We can trace this expansion back, using observations of the cosmic microwave background radiation and the abundance of light elements, to a point about 13.8 billion years ago. However, the theory itself doesn't describe what caused this state, nor does it truly account for the conditions at the very instant of the Big Bang, often referred to as a singularity. At this point, our current laws of physics, particularly general relativity, break down. This breakdown is a strong indication that we are missing a piece of the puzzle, a deeper understanding that might extend beyond the point where our current models cease to be valid. The idea that the universe existed before the Big Bang isn't a rejection of the Big Bang itself, but rather an expansion of our conceptual framework. Think of it like discovering that the foundation of a magnificent building was laid long before the visible structure began to rise. Scientists are exploring several theoretical avenues to describe this pre-Big Bang epoch. One prominent idea is that the Big Bang was not an absolute beginning, but a transition. Imagine a previous universe that reached a maximum size, then began to contract, eventually collapsing in on itself. This collapse wouldn't necessarily lead to annihilation, but perhaps to a bounce, a moment of extreme density and pressure from which a new phase of expansion, our Big Bang, emerged. This cyclic cosmology model, supported by theories like loop quantum cosmology, proposes an eternal cycle of expansion and contraction, a cosmic breath that has been going on for an immeasurable duration. In this view, our universe is but one iteration in an endless series. Another compelling possibility arises from quantum mechanics. At the incredibly small scales relevant to the very earliest moments, quantum fluctuations, tiny, random variations in energy and matter, become dominant. Some theories suggest that our entire universe could have emerged from such a quantum fluctuation in a pre-existing state, perhaps a quantum vacuum. This vacuum, however, would not be empty in the way we typically imagine nothingness. It would be a dynamic, energetic realm teeming with potential. The laws of physics, as we understand them, might have been fundamentally different, or perhaps not even yet formed in this primordial state. This perspective challenges our intuitive linear perception of time, suggesting that time itself might have begun with the Big Bang, and therefore, the concept of before is difficult to apply in a conventional sense. Yet the very existence of this energetic vacuum, capable of birthing a universe, implies a prior state, a stage upon which this cosmic drama could unfold. Furthermore, the concept of a multiverse offers another lens through which to view pre-Big Bang existence. If our universe is just one bubble in a vast, perhaps infinite, collection of universes, then the Big Bang could be the specific event that initiated our particular bubble. The parent reality from which our universe emerged could be a far grander, more complex structure, governed by different principles, or perhaps even generating universes through processes we can only dimly imagine. Theories like eternal inflation, a refinement of the inflationary model that describes the rapid expansion of the early universe, suggests that inflation, once started, may never stop everywhere, constantly spawning new bubble universes. In this scenario, the Big Bang is not a singular, unique event, but a localized genesis within a much larger, eternal cosmic tapestry. The exploration of what came before the Big Bang is not just an intellectual exercise. It's a profound journey into the nature of existence itself. It encourages us to question our most fundamental assumptions about beginnings and endings, about time and space. It reminds us that our current understanding, while remarkable, is a snapshot, a still point in an ongoing, perhaps eternal, cosmic narrative. The universe, in its immensity and complexity, continues to inspire awe and wonder, offering us a perspective that can gently dissolve the anxieties of our everyday lives. This contemplation of a universe that may have always been in some form offers a deep sense of continuity. The Big Bang was not the beginning of everything. While the Big Bang theory is our most robust scientific model for the origin and evolution of the observable universe, it describes the expansion of space from an incredibly hot and dense state, rather than an absolute beginning from a true void. Imagine it not as an explosion asterisk in asterisk space, but as the rapid expansion asterisk of asterisk space itself. The singularity, often associated with the Big Bang, is more accurately understood as a point where our current laws of physics, particularly general relativity, break down. It represents a limit to our understanding, a boundary beyond which our predictive models cease to function. This implies that what existed before this extremely dense and hot phase, or whether before, even has meaning in the absence of time as we know it, remains one of the most profound unanswered questions in cosmology. Scientists are exploring various theoretical frameworks, such as cyclic models, where the universe might undergo endless cycles of expansion and contraction, or theories suggesting our universe emerged from a pre-existing quantum vacuum. These ideas propose that the Big Bang was a transition, a momentous event within a larger, perhaps eternal cosmic landscape. It was the dawn of our asterisk observable universe, the moment from which space, time, matter, and energy began to evolve into the cosmos we see today, but not necessarily the absolute genesis of all existence. The universe, in its grandest sense, may be far older and more complex than our current observational horizon allows us to perceive directly. The Big Bang marks a crucial turning point, a phase transition of cosmic proportions, but the ultimate origin story is still being written in the whispers of quantum mechanics and the vastness of theoretical possibility. It's a reminder that our current snapshot of existence is just one chapter in a potentially infinite cosmic narrative. Even in the grandest expansion, a seed of what came before may still quietly reside. Our universe might be one of many in a multiverse. The idea that our vast cosmos, with its billions of galaxies and trillions of stars, might not be the only one, is a concept that stretches the very fabric of our understanding. It's a notion born not from science fiction, but from the rigorous application of physics and cosmology, particularly in the realm of understanding the universe's earliest moments. One of the most compelling avenues leading to the multiverse hypothesis arises from the theory of cosmic inflation. Inflation, a period of incredibly rapid expansion thought to have occurred fractions of a second after the Big Bang, elegantly explains several puzzling features of our universe, such as its remarkable flatness and the uniformity of the cosmic microwave background radiation. However, many models of inflation suggest that this process might not have ended everywhere simultaneously. Instead, inflation could be eternal, continuing indefinitely in some regions of spacetime. As inflation continues in these distant, unseen realms, it could spawn new bubble universes, each potentially with its own unique set of physical laws, constants, and even dimensions. Our observable universe would then be just one such bubble, having ceased its inflationary expansion at a particular point, allowing the familiar laws of physics to take hold within its boundaries. This concept, often referred to as eternal inflation or the multiverse of bubble universes, paints a picture of an unimaginably grander reality, a cosmic foam where countless universes are constantly being born, evolving, and perhaps even dying, all within a larger, eternally inflating space-time. Another path to the multiverse comes from quantum mechanics. The famous many worlds interpretation of quantum mechanics, proposed by Hugh Everett III, suggests that every time a quantum measurement is made, the universe splits into multiple branches, with each branch representing a different possible outcome of that measurement. While this interpretation is a way to resolve the paradoxes of quantum superposition without invoking wave function collapse, it implies a continuous branching of reality, leading to an unfathomably vast number of parallel universes. In this view, every decision, every random quantum event, creates new universes where all possible outcomes are realized. String theory, our current best candidate for a unified theory of everything, also hints at the possibility of multiple universes. String theory suggests that there are more than the 4 dimensions we perceive, 3 spatial, 1 temporal. These extra dimensions are thought to be curled up very small, but in some scenarios they could be large, allowing for the existence of other brains. Essentially, our universe could be a 3-dimensional brain floating in a higher dimensional space. Other brains in this space could represent other universes, potentially interacting with ours in subtle ways or remaining entirely separate. The sheer number of possible ways these extra dimensions can be curled up, known as the landscape of string theory, suggests an enormous number of possible universes, each with different fundamental constants and particle content. The implications of a multiverse are profound. If our universe is just one among many, then the fine-tuning of our universe's physical constants, the precise values that allow for the existence of stars, planets, and life, might be explained not by intelligent design, but by a statistical inevitability. In an infinite or vast collection of universes, it's not surprising that at least one, by chance, would possess the right conditions for life to emerge. This anthropic principle suggests that we observe the universe to be the way it is because, if it were different, we wouldn't be here to observe it. The existence of a multiverse shifts our perspective from a unique, singular origin story to a more humble place within a grander cosmic tapestry. The possibility of other universes, each with its own unique story, reminds us that our current understanding is just a glimpse, a single frame in an unimaginably vast film. And in this vastness, the thought of other realities, other possibilities, can be a gentle whisper in the quiet of the night, reminding us of the boundless wonder that may lie beyond our immediate perception. Quantum fluctuations could have birthed our universe. Imagine, if you will, a canvas of pure potential, a realm where existence itself is not yet solid, but a vibrant, energetic dance of possibilities. This is the realm of quantum fluctuations, the tiny, fleeting, and utterly fundamental ripples that can arise in the very fabric of spacetime, even in what we might consider empty space. These are not mere disturbances, but the very essence of quantum reality, where probabilities hold sway and the seemingly impossible can, and does, happen. In the context of the Big Bang, many cosmological models suggest that our universe did not begin as a preformed entity, but rather emerged from such a quantum fluctuation. Think of it as a spontaneous spark, a tiny, improbable excrescence from a state of profound non-existence, or perhaps from a pre-existing, different kind of reality. This fluctuation, born from the inherent uncertainty and dynamism of the quantum world, would have been infinitesimally small, perhaps even smaller than a single point, but it would have contained within it the seeds of everything that was to come. The quantum vacuum, often misunderstood as a void, is in fact a bustling sea of activity. According to quantum field theory, virtual particles are constantly popping into and out of existence, a phenomenon that can be measured and observed through its effects. These are not particles that persist, but fleeting existences, borrowing energy from the vacuum for a brief moment before annihilating each other. However, under specific conditions, it's theorized that such a fluctuation could have occurred on a scale large enough, or with sufficient energy, to initiate a process of rapid expansion. This initial fluctuation, this quantum event horizon, would have been the genesis, the microscopic origin point from which the vast cosmos we inhabit began to unfurl. It's a concept that challenges our intuitive understanding of beginnings, suggesting that even the most profound events can arise from the smallest, most ephemeral of causes. The idea is that in the incredibly dense and energetic conditions that may have preceded the Big Bang, or in a state from which the Big Bang arose, the quantum vacuum was not stable. It was a state prone to instability, where a random fluctuation could, by sheer chance, begin to grow. This growing fluctuation would have been a region of slightly higher energy density, and this difference would have caused it to expand. As it expanded, it would have brought more of the underlying quantum field into play, leading to a runaway process. This is where the concept of cosmic inflation often comes into play. Inflation proposes a period of extremely rapid expansion in the very early universe, a timescale of fractions of a second during which the universe grew by an almost unimaginable factor. This inflationary period is thought to have been triggered and sustained by the energy inherent in the quantum field itself, a field that was initially disturbed by that primordial fluctuation. So the universe in this view didn't begin in a classical sense, but rather emerged or inflated from a quantum state. It's like a bubble forming on the surface of a boiling liquid. The bubble isn't there from the start, but arises from the inherent energy and motion within the liquid. The quantum fluctuation is that initial, improbable bubble, and inflation is the rapid expansion that follows. This explains why the universe appears so uniform and flat on large scales. The inflationary period would have smoothed out any initial irregularities, stretching the quantum fluctuations to immense sizes, and making the universe appear incredibly uniform. The tiny, almost insignificant quantum ripples present in that initial state would have been stretched and magnified to become the seeds of the large-scale structures we observe today, like galaxies and clusters of galaxies. The beauty of this idea lies in its grounding in quantum mechanics, the most successful theory we have for describing the universe at its most fundamental level. It suggests that the grandest of cosmic events, the very origin of our reality, might be a direct consequence of the inherent probabilistic nature of existence. It's a profound thought that the immense tapestry of the cosmos, with all its stars, planets, and galaxies, could have sprung from a spontaneous, quantum-level accident. An accident, perhaps, in the most majestic and meaningful sense of the word. It's a testament to the power of the very small to give rise to the unimaginably large, a whisper of potential blooming into a cosmic roar. From the ephemeral tremor of quantum possibility, a universe began to bloom. Cyclic models suggest a universe that expands and contracts. Imagine, for a moment, that the grand unfolding of our universe, the magnificent expansion we observe, is not a singular event, but rather a recurring rhythm, a cosmic breath. Cyclic models, a fascinating family of cosmological theories, propose just this: a universe that doesn't just begin and then continue to expand indefinitely, but one that undergoes endless cycles of expansion and contraction, a perpetual ebb and flow. These models offer a compelling alternative to the standard Big Bang narrative, suggesting that what we perceive as the Big Bang might have been a bounce from a previous, contracting phase of the cosmos. At its heart, the idea is elegantly simple, yet profoundly complex to model. Instead of a singular point of infinite density and temperature, a singularity from which everything emerged, cyclic models often posit a transition point. Think of it like this: the universe expands, reaches a maximum size, and then, due to the relentless pull of gravity or some other intrinsic property, begins to contract. This contraction continues, gathering all matter and energy into an increasingly dense and hot state, not quite a singularity, but a highly compressed phase. Then, through a mechanism that varies between different cyclic models, this compressed state bounces back, initiating a new phase of expansion, a new Big Bang. One of the most prominent examples of a cyclic model is the Big Bounce scenario, often explored within the framework of loop quantum cosmology. In this view, the fundamental fabric of spacetime is not infinitely divisible, but rather composed of discrete units. As the universe contracts, it reaches a point where these quantum units resist further compression, creating a repulsive force that triggers the bounce. This avoids the problematic singularity of the standard Big Bang model, where our current laws of physics break down. Another approach comes from string theory, particularly theories involving brains' higher-dimensional objects. In some brain world scenarios, our universe might be a three-dimensional brain existing within a higher-dimensional space. Collisions or interactions between these brains could be the cosmic events that trigger new cycles of expansion. Imagine two sheets of paper, constantly moving, occasionally bumping into each other, and each collision creating a new ripple of existence. The appeal of cyclic models lies in their ability to address some of the lingering questions in cosmology. For instance, they can potentially explain the homogeneity and isotropy of the universe, why it appears so uniform in all directions. In a contracting phase, all parts of the universe are brought into close proximity, allowing for thermal equilibrium to be established before the expansion begins. They also offer a way to circumvent the horizon problem, the puzzle of why distant regions of the universe, which have never been in causal contact, have the same temperature. However, these models are not without their challenges. A significant hurdle is the entropy problem. According to the second law of thermodynamics, entropy, or disorder, always increases in a closed system. If the universe undergoes endless cycles, each cycle should accumulate more entropy than the last. This would mean that each subsequent expansion would be longer and more chaotic than the one before it, leading to a universe that, over time, becomes increasingly disordered and eventually unable to support complex structures. Some cyclic models propose mechanisms to reset or dilute entropy at the bounce, but these are active areas of research. Furthermore, the precise physical mechanisms that drive the contraction and, crucially, the bounce itself, are still subjects of intense theoretical investigation. What force or quantum effect can overcome the immense gravitational pull during contraction and initiate a new expansion? Different models propose different solutions, ranging from modifications to gravity at extreme densities to exotic forms of matter or energy. The implications of cyclic cosmology are profound. If our universe is part of an eternal cycle, then the Big Bang was not an absolute beginning, but a transition. The concept of time itself might be cyclical rather than linear. Our existence in this grand cosmic dance would be but one iteration in an infinite series, a fleeting moment in a story that has no true start or end. It shifts our perspective from a universe with a definitive origin to one that is perpetually renewing itself, a testament to the universe's enduring capacity for transformation. The universe, in its grand cosmic breath, inhales and exhales, a rhythm of becoming and rebecoming, a timeless dance of existence. The concept of time may not have existed before the Big Bang. Imagine, if you will, a state so fundamentally different from our current reality that the very framework of existence as we understand it simply wasn't there. Our most profound scientific theories, particularly Einstein's theory of general relativity, describe the universe as a unified fabric of spacetime. This spacetime is dynamic, interwoven, and it's within this fabric that all events unfold, all changes occur, and what we perceive as time flows. However, when we extrapolate backwards towards the extreme conditions of the Big Bang, the equations of general relativity begin to break down. They point towards a singularity, a point of infinite density and temperature, where the very concepts of space and time as we know them cease to have meaning. In this context, asking what happened before time began becomes a question that might be fundamentally unanswerable within our current understanding, because the prerequisite for happening, the existence of time itself, may not have been present. Consider the very nature of time as we experience it. It's a unidirectional flow, a sequence of moments from past to present to future. This sequence, this progression, is intrinsically linked to change, to motion, to the very processes that define our universe. If we imagine a state prior to the Big Bang, a state perhaps of pure potential, or an entirely different phase of cosmic existence, it's conceivable that such a state lacked the conditions necessary for the emergence of temporal progression. Without the expansion of space, without the interactions of matter and energy that give rise to the arrow of time, the very notion of a before or after would be meaningless. Some cosmological models, like those that propose a bounce rather than a singular beginning, suggest that the universe might have contracted to an incredibly dense state and then re-expanded. In such scenarios, the time of the contracting phase would be running in reverse relative to our current time, or perhaps time itself would have behaved in ways we can't yet comprehend. The question then becomes not just about what existed before asterisk time, but whether the very concept of time is an emergent property of our particular cosmic epoch, one that might not have been a feature of any prior state. It challenges our deep-seated intuition that time is an absolute, unchanging backdrop against which the universe plays out. Instead, it suggests that time, like space, might be a component of the universe that came into being with the Big Bang, or perhaps even emerged from a more fundamental, timeless reality. This perspective invites us to consider that our current experience of time is a specific manifestation, a particular way in which existence is structured, and that other structures, other realities, might exist or have existed without this familiar temporal dimension. It is a profound philosophical and scientific puzzle, pushing the boundaries of our imagination and our understanding of reality itself. And so, the familiar rhythm of moments may have found its first beat only as the universe began its grand unfolding. The singularity of the Big Bang is a point of mathematical breakdown. Imagine, if you will, a concept so profound, so utterly fundamental to our understanding of the cosmos, that it pushes the very limits of our current scientific language. We speak of the Big Bang, that moment often depicted as the explosive genesis of our universe. But as we peer closer, as we attempt to describe the infinitesimally small moments at asterisk the very instant of this cosmic dawn, our most sophisticated mathematical tools begin to falter, to break down. This point, where all the matter and energy of our observable universe is thought to have been compressed into an infinitely small, infinitely dense speck, is known as the singularity. It is a theoretical construct, a place where our equations, designed to describe the workings of spacetime and gravity, cease to provide coherent answers. When we try to plug in the values, infinite density, infinite temperature, infinite curvature of spacetime, the mathematics simply gives up. It's like trying to divide by zero. The operation becomes undefined, meaningless within the framework of our current understanding. This isn't a sign that the universe is inherently illogical, but rather a potent signal that our current models, particularly Einstein's theory of general relativity, are incomplete. General relativity, while remarkably successful at describing gravity on large scales, struggles to reconcile itself with the bizarre rules of quantum mechanics, the physics that governs the very small. At the singularity, both gravity and quantum effects are expected to be overwhelmingly dominant, and the theories that describe them separately no longer offer a unified picture. Physicists believe that a new theory, a theory of quantum gravity, is needed to truly understand what happens at these extreme conditions. Such a theory would, in principle, be able to describe the universe not just before, but at the very moment of its birth, potentially resolving the paradox of the singularity. It suggests that the beginning, as we envision it, a sharp, instantaneous event, might be a simplification, a placeholder for a more complex and perhaps continuous process that our current mathematics cannot yet fully grasp. The breakdown of our mathematics at the singularity is not an endpoint to our inquiry, but a vibrant invitation to explore deeper, to seek new paradigms that can bridge the gap between the cosmic and the quantum, the vast and the infinitesimally small. It is a testament to the humbling nature of scientific discovery, reminding us that even in the most fundamental questions, there are still vast frontiers of the unknown, waiting to be illuminated. This mathematical breakdown is a signpost, pointing us towards a more complete, more elegant description of reality, a reality that may be far stranger and more beautiful than we can currently imagine, a reality where the very concept of a singular beginning might itself be reevaluated. It signifies that our current understanding of space and time, so reliable in our everyday experience, may not apply at the absolute genesis of existence, forcing us to confront the limitations of our current descriptive powers and the profound mysteries that lie at the very edge of our comprehension. In the face of such mathematical silence, we find not an end, but a quiet invitation to wonder about the very fabric of what was and what is to be. String theory offers potential insights into pre-Big Bang physics. Imagine, if you will, a universe not of point-like particles, but of tiny, vibrating strings. These are not the strings of a violin, nor the strings of a puppet master, but fundamental entities, unimaginably small, existing in dimensions beyond our everyday three spatial ones, perhaps 10 or 11 in total. This is the elegant, albeit complex, framework of string theory. It proposes that the fundamental constituents of the universe, the very building blocks of matter and energy, are not discrete particles like electrons and quarks, but rather one-dimensional vibrating strings. The different ways these strings vibrate, their frequencies and amplitudes, determine the properties of the particles we observe. A string vibrating in one pattern might manifest as an electron, while a different vibration could give rise to a photon or a graviton, the hypothetical particle mediating gravity. This is a profound unification, suggesting that all the diverse forces and particles in the universe are simply different notes played by these fundamental strings. Now, how does this relate to what might have existed before the Big Bang? String theory, in its various formulations, often encounters a singularity when trying to describe the very beginning of the universe, much like other cosmological models. However, the presence of these fundamental strings and extra dimensions offers a potential way around this. Instead of a point of infinite density and temperature, a singularity, string theory suggests that the universe might have undergone a bounce. Imagine two branes, which are higher dimensional surfaces within the larger string theory landscape, approaching each other. As they get incredibly close, instead of colliding and creating a singular point, they might bounce off each other, initiating a new phase of expansion. This brane bounce scenario offers a compelling alternative to the traditional Big Bang singularity. The universe in this view did not begin from an infinitely dense point, but rather transitioned from a previous contracting phase into our current expanding universe. This implies a continuity, a cosmic cycle, where the end of one universe, or at least one phase of cosmic existence, becomes the beginning of another. The energy that drives this bounce and the subsequent expansion could be understood within the framework of string theory's complex energy dynamics. Furthermore, the extra dimensions proposed by string theory could play a crucial role. They might provide the space or the energetic landscape for these branes to interact and bounce. The very fabric of space-time, as described by string theory, could have existed in a different configuration before our current universe's expansion began. The gravitational interactions within this higher dimensional framework could have prevented a true singularity, allowing for a smooth transition from a contracting to an expanding phase. The theory also grapples with the nature of time itself. In some string theory scenarios, time might not be a fundamental, linear progression as we perceive it. It could be an emergent property, arising from the interactions and vibrations of these fundamental strings. This could mean that the very concept of before the Big Bang, in our conventional understanding of time, might not even be applicable. The universe could have existed in a timeless or cyclically timed state, a state of potentiality from which our current temporal reality emerged. The challenge, of course, lies in finding observable evidence to support these highly theoretical concepts. Physicists are exploring potential signatures of string theory in the cosmic microwave background radiation, or in the very early universe's particle physics, though these are extremely subtle and difficult to detect. Nevertheless, string theory provides a rich theoretical playground for exploring these profound questions about cosmic origins, offering a glimpse into a universe that might be far more interconnected and cyclical than our current, simpler models suggest. It paints a picture of a cosmos that is not born from nothingness in a singular moment, but rather a continuous unfolding, a grand cosmic dance of vibrating strings and evolving dimensions. Thus, the universe may be a symphony of vibrations, eternally echoing through dimensions we cannot yet perceive. Loop quantum cosmology provides an alternative to the singularity. Imagine, for a moment, a universe not born from an infinitely dense point, a singularity, which is a place where our current understanding of physics breaks down. Instead, consider a different narrative, one offered by a fascinating field called loop quantum cosmology. This approach doesn't shy away from the extreme conditions of the early universe, but it reinterprets them. Instead of an infinite density, loop quantum cosmology suggests that the universe reached a point of maximum, but finite, density. Think of it like squeezing a balloon as much as you possibly can. It gets incredibly small and dense, but it doesn't vanish into an infinitely small point. At the heart of this theory is the idea that space and time themselves are not continuous, smooth fabrics, but are actually granular, made up of discrete, fundamental loops or quanta. These are the smallest possible units of space and time, indivisible and fundamental. So, as the universe contracts towards this maximum density, these loops become incredibly tightly packed. But crucially, they can't be squeezed any further. It's like trying to pack more and more grains of sand into a tiny box. Eventually, you can't fit any more. In this analogy, the box represents the fundamental limit of space-time. When the universe reaches this point of maximum finite density, instead of collapsing into a singularity, it bounces. This is the Big Bounce scenario. The universe stops contracting and begins to expand, leading to the universe we observe today. This bounce is not a violent, instantaneous event in the way a singularity might be conceived. Instead, it's a consequence of the fundamental quantum nature of space-time itself. The very fabric of reality, at its most basic level, prevents an infinite collapse. This concept of a bounce is profoundly significant. It means that the Big Bang might not have been a beginning from nothing, but rather a transition from a contracting phase of a previous cosmic epoch to the expanding phase of our current universe. This offers a way to avoid the mathematical and conceptual problems associated with the singularity in the standard Big Bang model. It suggests a continuous, albeit cyclical, existence for the universe, where the end of one era is the beginning of another. Furthermore, loop quantum cosmology also proposes that information might be preserved across this bounce. This is a crucial point because the idea of a singularity often implies that all information about what came before is lost. But if there's a bounce, then the state of the universe just before the maximum density could potentially influence the state of the universe just after. This opens up the possibility that our current universe is not entirely new, but carries echoes or remnants of a prior cosmic existence. It's like a river that flows, reaches a point where it seems to disappear into the earth, only to re-emerge further downstream, carrying with it the essence of its journey. The elegance of loop quantum cosmology lies in its attempt to unify gravity with quantum mechanics, a challenge that has eluded physicists for decades. By quantizing space-time itself, it offers a framework where the extreme conditions of the early universe can be described without resorting to infinities. It paints a picture of a universe that is not only vast and wondrous, but also has a deep, perhaps cyclical, history that predates our current understanding. It's a universe that is constantly evolving, even at its most fundamental level, and this evolution is driven by the very quantum nature of its being. The idea of a bounce suggests that the universe has a resilience, a capacity to transform and renew, rather than simply beginning and ending. It's a more dynamic and perhaps more hopeful view of cosmic origins, where the end is not an end, but a transformation into a new beginning. This perspective allows us to contemplate a universe that has always been, in some form, existing and transforming, a testament to the enduring power of cosmic cycles and the fundamental quantum fabric that underpins all existence. The universe, in its most fundamental weave, offers a cyclical breath, a gentle bounce from an ancient past into the quiet wonder of today. The cosmic egg analogy hints at a compressed prior state. Imagine, if you will, a time before the grand unfolding, a state so condensed, so profoundly unified, that our current understanding of space and time simply cannot grasp it. This is where the evocative, though admittedly simplified, analogy of the cosmic egg finds its resonance. It suggests not a literal ovum, but a metaphorical representation of a state where all the fundamental forces, all the particles, All the potential of our universe was held in an unimaginably dense and compact form. Think of it as a single point, a singularity, not necessarily in the explosive sense of the Big Bang itself, but as a point of ultimate compression, a state where the very fabric of reality, as we perceive it, was squeezed to its absolute limit. This compressed state, this cosmic egg, is not a void, but rather a realm of immense potential energy, a seed holding within it the blueprints for everything that would eventually emerge. It's a concept that challenges our intuitive understanding of beginnings, suggesting that the universe didn't spring from nothing, but rather from a state of extreme concentration. This idea is not a new one. Ancient cosmologies across cultures have grappled with similar notions of a primordial, undifferentiated state from which the cosmos arose. Modern physics, in its own sophisticated language, echoes these ancient intuitions. Theories exploring what might have preceded the Big Bang often describe a phase of extreme density and temperature, a period where the universe was incredibly small. While the traditional Big Bang model begins with a singularity, some contemporary theories, like cyclic universe models or certain interpretations of loop quantum cosmology, propose a bounce, a transition from a contracting phase of a previous universe to the expanding phase we observe today. In these models, the cosmic egg is not a static starting point, but a dynamic transition phase, a moment of ultimate compression before a powerful rebound. It's a state where the fundamental forces, which are distinct today, might have been unified, a single, all-encompassing force. The very concept of before the Big Bang becomes problematic because time itself, as we understand it, is thought to have begun with the Big Bang. So this pre-Big Bang state, this cosmic egg, exists in a realm where our familiar notions of past, present, and future may not apply. It's a profound mystery, a whisper of an origin that is less about a sudden eruption and more about a transformation from an incredibly dense, unified state into the vast, expanding cosmos we inhabit. It's a reminder that the universe's story may be far older and more complex than a single, explosive beginning. Within this compressed potential, the universe slumbered, a silent promise waiting for its moment of emergence. Information might have survived the transition from a previous universe. The very notion of information, that intangible essence of order and structure, surviving the cataclysmic event we call the Big Bang, is a profound, and for many, a counterintuitive idea. Our common understanding of the Big Bang is one of absolute beginnings, a point from which all that we observe, all matter, energy, space, and time, emerged from an infinitely dense, infinitesimally small singularity. In this view, anything that existed before is, by definition, gone, erased, or simply irrelevant to our current cosmic reality. However, some of the most advanced theoretical frameworks in physics, particularly those exploring the cyclical nature of the universe or the possibility of a multiverse, suggest that this might not be the case. These models propose that the Big Bang was not an absolute creation ex nihilo, but rather a transition, a phase change from a prior state. If it was a transition, then the question of what persists across that transition becomes paramount. Consider the concept of information in physics. It's not just about data in a computer. It's about the fundamental properties of particles, their arrangements, their interactions, and the very laws that govern them. In quantum mechanics, for instance, information is conserved. The famous black hole information paradox grapples with this very idea. What happens to the information encoded in matter that falls into a black hole? While the popular narrative often suggests it's lost forever, many physicists believe that information must somehow be preserved, perhaps encoded in Hawking radiation or in the very structure of space-time. If information is so fundamental that it's believed to be conserved even in the extreme environment of a black hole, it's not an unreasonable leap to consider its potential survival through a cosmic transition. Cyclic universe models, such as those inspired by string theory or loop quantum cosmology, often involve a big bounce rather than a singularity. In these scenarios, a previous universe, perhaps in a state of extreme contraction, reaches a minimum size and then bounces back, expanding to become our current universe. If such a bounce occurs, it's conceivable that certain fundamental aspects of the universe, such as its underlying physical laws or even a residual imprint of its previous configuration, could persist. It's not necessarily about information in the sense of specific historical events, but rather about the fundamental constants, the symmetries, or the very fabric of reality that would dictate the initial conditions of the new expansion. Another avenue of thought comes from the idea of a meta-universe or multiverse. If our Big Bang was the birth of our specific universe from a larger, perhaps eternal cosmic substrate, then the information that defines our universe, its particular set of physical laws and constants, could be seen as a subset of a grander, pre-existing informational structure. Imagine a vast, cosmic ocean of potentiality. Our Big Bang might be the moment a specific ripple, a unique configuration, began to grow and evolve into our observable reality. The underlying rules of that ocean, the fundamental principles of this meta-universe, would have been in place before our specific universe came into being. The challenge lies in defining what kind of information could possibly survive. It's unlikely to be detailed historical records of a previous cosmic epoch. Instead, it might be more akin to the fundamental mathematical structures or quantum fields that underpin reality itself. Think of it like this. If you were to melt down a complex statue and recast it into a new form, the bronze itself, the fundamental material, would survive. In a similar, albeit vastly more abstract, way, the fundamental constituents or principles of reality might persist, dictating the initial conditions of our universe's expansion. This is a realm where physics meets philosophy, where our understanding of causality and existence is stretched to its limits. The idea that our universe is not entirely sui generis, but carries a faint echo or a foundational inheritance from whatever came before, adds a layer of deep continuity to the grand cosmic narrative, suggesting that even in apparent beginnings, there are threads of ancient connection. And so, the possibility that a whisper of what was, a fundamental blueprint, may have guided the first moments of our existence, reminds us that the universe is a tapestry woven with threads of both radical newness and enduring continuity. The laws of physics as we know them may have been different before. Imagine, if you will, a realm where the very rules that govern our existence, gravity, electromagnetism, the nuclear forces, were not yet solidified, not yet etched into the fabric of spacetime as we understand them. Before the Big Bang, in the moments, or perhaps eons, preceding that grand cosmic unfolding, the fundamental constants that define our universe might have been in a state of flux, or perhaps entirely different. Our current understanding of physics is built upon observations of the universe asterisk after asterisk. It had cooled and expanded sufficiently for these laws to manifest in a stable, predictable manner. The extreme conditions of the very early universe, and any potential precursor state, are beyond the reach of our direct observation and even our most sophisticated theoretical models. For instance, consider the speed of light, a seemingly immutable constant in our universe. What if, in a pre-Big Bang era, this speed was not constant, or even vastly different? Or what about the gravitational constant, the very force that holds galaxies together and dictates the orbits of planets? Could it have possessed a different magnitude, leading to a universe that either collapsed immediately or expanded too rapidly to form structure? The strong nuclear force, responsible for binding atomic nuclei, and the weak nuclear force, governing radioactive decay, are also candidates for having had different characteristics. Theoretical frameworks like string theory and loop quantum cosmology attempt to address these profound questions. String theory, for example, posits that fundamental particles are not point-like, but rather tiny vibrating strings, and the specific way these strings vibrate determines the properties of the particles and the forces they mediate. In this context, the laws of physics would emerge from the particular configuration and dynamics of these underlying strings, which could have been different in a pre-Big Bang state. Similarly, loop quantum cosmology suggests that spacetime itself is quantized, made up of discrete units. The interactions and geometry of these fundamental units could have dictated a different set of physical laws before the universe underwent its dramatic expansion. The very concept of laws implies a degree of permanence and universality. However, in the context of origins, it is more accurate to speak of emergent properties. What we perceive as fundamental laws might be the stable, macroscopic manifestations of deeper, more fundamental principles that were themselves in a nascent or inchoate state before the Big Bang. It is possible that the universe underwent a phase transition, much like water freezing into ice or boiling into steam, where the underlying energetic conditions shifted, causing the fundamental forces and constants to settle into their current configurations. This idea is not about randomness, but about a different kind of order, one that predates the familiar order we experience. It is the order of potential, of possibilities yet to be realized. The universe, in its earliest, perhaps infinitely dense and hot state, was a realm of pure potential, where the very definitions of mass, energy, charge, and force were perhaps fluid, waiting for the cosmic dawn to give them form and permanence. Our current laws are the enduring echoes of that initial crystallization, a testament to the universe's journey from an unimaginable precursor to the structured cosmos we inhabit. And so, the laws we hold as absolute might be but one specific manifestation, a particular melody in an infinite symphony of cosmic possibilities, born from a time when the very notes were still being composed. Dark energy could be a remnant of a previous cosmic epoch. The universe we observe today is characterized by a mysterious force known as dark energy, which is responsible for its accelerating expansion. While we often associate this phenomenon with the aftermath of the Big Bang, a fascinating and deeply philosophical line of inquiry suggests that dark energy might not be an entirely new player on the cosmic stage, but rather an echo, a lingering whisper from a time that predates our current cosmic era. Imagine, if you will, that the universe has undergone cycles of expansion and contraction, perhaps even before the event we call the Big Bang. In such a cyclical model, the immense pressures and energies of a collapsing universe could have left behind a residual energy field, a sort of cosmic sediment, that is now manifesting as the dark energy we detect today. This concept challenges our linear perception of time and causality, suggesting that the universe's story is far richer and more complex than a single, definitive beginning. Consider the possibility that the universe, in a previous iteration, reached a point of maximum expansion, perhaps even exceeding the current scale, and then began to contract. This contraction would have been a violent, high-energy event, compressing matter and energy to an unimaginable density. However, it is conceivable that not all of this energy would have been consumed or annihilated in the subsequent bounce or transition into our current Big Bang phase. Some portion of this primordial energy, perhaps in a form that is not easily detectable by our current instruments, or that has fundamentally altered its nature over eons, could have persisted. This persistent energy, interwoven with the fabric of spacetime itself, might be what we now perceive as dark energy. It's a subtle but pervasive influence, gently pushing galaxies apart, a constant reminder of a past that may have shaped our present in ways we are only beginning to comprehend. The very nature of dark energy, its uniform distribution throughout the cosmos, and its seemingly constant density as the universe expands, hints at a fundamental property of spacetime itself, rather than a fleeting phenomenon associated solely with the Big Bang. If dark energy were merely a byproduct of the initial expansion, one might expect its influence to wane over time, or to be unevenly distributed. Instead, it appears to be an intrinsic characteristic of the universe, driving its evolution with an unwavering force. This suggests a deeper, more ancient origin, a connection to the very essence of existence that transcends the specific event of our Big Bang. It's as if the universe carries within it the scars, or perhaps the enduring essence, of prior cosmic lives. Furthermore, some theoretical models propose that the Big Bang itself was not a singular point of creation from absolute nothingness, but rather a transition from a pre-existing state. In these models, the universe might have undergone a bounce, where a contracting universe reached a minimum size and then began to expand again, giving rise to our current observable cosmos. If such a bounce occurred, the energy density of the universe just before the bounce, and the mechanisms that facilitated the transition, could have imprinted a persistent energetic signature onto the newly forming universe. This signature, manifesting as a cosmological constant or a dynamic field, would be what we now identify as dark energy. It's a notion that imbues our universe with a sense of continuity, a grand cosmic lineage stretching back into an unfathomable past. The implications of dark energy being a remnant from a previous cosmic epoch are profound. It suggests that the universe is not a singular, isolated event, but part of a potentially infinite sequence of cosmic cycles. Our Big Bang, in this view, is not the ultimate beginning, but rather a chapter in a much larger, ongoing narrative. This perspective can offer a sense of solace and perspective, reminding us that even the grandest phenomena we observe are part of a continuous, evolving tapestry of existence. The accelerating expansion, driven by dark energy, then becomes not a sign of impending doom, but a natural phase in a cosmic dance that has been going on for an immeasurable span of time, and may continue for eons yet to come. And so, this lingering force, this gentle push outwards, may be the quiet memory of a universe that once was, a subtle testament to the enduring power of cosmic cycles. Inflationary cosmology might have roots in a pre-Big Bang phase. The idea of cosmic inflation, a period of incredibly rapid expansion in the earliest moments of our universe, is a cornerstone of modern cosmology. But what if this explosive growth, this sudden stretching of space-time, wasn't an isolated event, but rather a reverberation, a continuation, or even a consequence of a state that existed before the Big Bang as we typically conceive it? This is where the fascinating interplay between inflationary theory and the mysteries of pre-Big Bang physics truly comes alive. Inflationary cosmology proposed to solve several perplexing problems with the standard Big Bang model, such as the horizon problem. Why is the universe so uniform on large scales? The flatness problem. Why is the universe so geometrically flat? And the monopole problem. Where are the predicted exotic particles? Suggests that in the first tiny fraction of a second after the Big Bang, the universe underwent an exponential expansion. This period of inflation, lasting perhaps from 10 to 32 seconds after the initial moment, would have stretched even the smallest quantum fluctuations to cosmic proportions, explaining the large-scale homogeneity and flatness we observe today. However, the very mechanisms that drive inflation, the hypothetical fields and energies involved, are often discussed in contexts that extend beyond the traditional Big Bang singularity. For instance, many inflationary models require a specific type of energy density, often called inflaton energy, which is thought to have dominated the universe during this epoch. The origin of this inflaton field and its associated energy is not intrinsically tied to the singularity itself. Instead, it's plausible that this field was already present, perhaps in a different configuration or state, in a pre-Big Bang universe. Imagine a vast, perhaps even timeless, expanse where quantum fields existed in a state of high potential energy. When this energy began to dissipate, it could have triggered the inflationary epoch, effectively birthing the observable universe as we know it. Consider models that propose a cyclic universe. In these scenarios, the universe undergoes endless cycles of expansion and contraction. A Big Bang might not be a singular beginning, but rather a bounce from a previous contracting phase. During the contraction, the universe would have become incredibly dense and hot, potentially reaching a state where quantum gravity effects become dominant. It's within this phase, or in the transition from contraction to expansion, that the conditions for inflation could be established. The energy that fuels inflation might then be a residual effect of the previous cosmic era, or a fundamental property of the quantum fields that persists through the cycle. Furthermore, some theories suggest that the inflationary epoch could have been initiated by the decay of a pre-existing, highly energetic state. This state might have been characterized by a different set of physical laws or a different dimensionality of space-time. The transition from this pre-existing state to the inflationary phase would then represent the beginning of our particular universe, but not necessarily the beginning of existence itself. In essence, the physics that drives inflation, the quantum fields, the vacuum energy, the very fabric of space-time, might have a lineage that predates the singularity, hinting at a cosmic continuity that stretches back into an unimaginable past. The power of inflationary cosmology, therefore, lies not just in explaining the early moments of our universe, but also in its potential to connect us to a much grander, and possibly eternal, cosmic narrative that began long before our own universe's apparent genesis. Thus, the explosive growth of our universe may well be an echo from a time before time itself began. The early universe's homogeneity suggests a prior unifying force. Imagine, if you will, looking back across the vast expanse of cosmic history, not just to the fiery birth of stars, but to the very instant after the Big Bang. What we observe, through the exquisite precision of our instruments, is a universe that is remarkably, almost impossibly, uniform in temperature. The cosmic microwave background radiation, that faint afterglow of creation, tells a story of incredible consistency across billions of light years. This uniformity, this astonishing lack of significant temperature variation, is known as homogeneity. Now, in the standard model of cosmology, this homogeneity is often explained by a period called cosmic inflation, a brief but explosive era of exponential expansion occurring fractions of a second after the Big Bang. Inflation, in essence, stretched out any initial irregularities to such an extent that they became virtually undetectable, smoothing out the nascent universe like a cosmic blanket. However, the very existence of this profound homogeneity raises a deeper question, a philosophical whisper from the fabric of reality itself. If the universe began as a chaotic, energetic soup, how did it become so perfectly, so uniformly smooth? The sheer scale of this uniformity, spanning a volume of space that would later give rise to countless galaxies, suggests that there might have been a governing principle, a fundamental force or condition that predated and perhaps even guided this early state. It's as if the universe, in its infancy, was imbued with a deep-seated order, a tendency towards sameness that transcends the immediate forces we understand. This isn't to say that inflation isn't a powerful explanation, but rather that the profoundness of the homogeneity it explains points towards something even more fundamental, a prior unity that allowed for such a consistent beginning. It hints at a state where distinctions were less pronounced, where the building blocks of everything were more intimately connected, perhaps existing in a single, unified state before the emergence of the diverse phenomena we see today. This uniformity, therefore, acts as a cosmic echo, resonating with the idea that before the grand unraveling of the universe into its myriad forms, there existed a state of profound, underlying connection, a unifying force that laid the groundwork for all that was to come. It's a testament to the elegant simplicity that often underpins the most complex systems, a quiet suggestion that the universe's initial state was one of profound, almost serene, togetherness. In the vast quiet of existence, this cosmic smoothness whispers of a unity that cradled all potential. The arrow of time is a mystery that might extend beyond the Big Bang. We perceive time as a unidirectional flow, a relentless march from past to future. This fundamental aspect of our experience, the arrow of time, is deeply ingrained, shaping our memories, our actions, and our very sense of self. Yet, when we delve into the fundamental laws of physics, this unidirectional flow is not so clearly defined. Many of the most basic equations governing the universe are time-symmetric, meaning they would work just as well if time ran backward. The reason we experience time moving forward and not in reverse is one of the deepest puzzles in cosmology and physics. The prevailing scientific explanation for this arrow of time is linked to the second law of thermodynamics, which states that the total entropy or disorder of a closed system can only increase over time. The universe, as a whole, is generally considered to be such a system. At the moment of the Big Bang, the universe was in an extraordinarily low entropy state, incredibly ordered and uniform. As the universe has expanded and evolved, its entropy has increased, leading to the formation of stars, galaxies, and all the complex structures we observe. This increase in disorder creates the perception of a temporal direction. However, this explanation raises a profound question. Why was the universe in such a low entropy state at its inception? If the Big Bang was the ultimate beginning, then the initial low entropy seems almost like a deliberate setup. This leads some physicists to consider whether the arrow of time might have its origins in a state or process that preceded the Big Bang itself. Could the conditions of the universe before the Big Bang, perhaps in a previous phase of expansion and contraction, or within a larger multiverse, have established the fundamental asymmetry that dictates our forward-moving temporal experience? Some theoretical models, like certain cyclic universe scenarios, propose that the universe undergoes endless cycles of expansion and contraction. If such a model is accurate, then the end of one universe, with its high entropy, might lead to a bounce into a new universe that begins in a low entropy state, thus perpetuating the arrow of time across cosmic epochs. Other theories, such as those emerging from string theory or loop quantum cosmology, suggest that the Big Bang singularity might be an illusion, a point where our current models break down, and that a more continuous, perhaps cyclical process was at play. In these scenarios, the arrow of time could be an emergent property of this larger, more enduring cosmic structure, rather than something that spontaneously began with our specific expansion phase. The very concept of time, as we understand it, is also deeply intertwined with the expansion of the universe. As space itself stretches, it creates the temporal dimension we experience. If the universe is part of a larger, perhaps eternal, structure, then our perception of a singular beginning and a unidirectional flow might be a localized phenomenon within a grander, timeless, or multi-temporal reality. Exploring the arrow of time beyond the Big Bang is not just an academic exercise. It touches upon our most fundamental understanding of reality, causality, and existence itself. It suggests that the seemingly simple passage of moments might be a whisper from a far vaster, more ancient cosmic story. The steady unfolding of moments, a river flowing ever onward, may be a timeless echo from a cosmic dawn we have yet to fully comprehend. The concept of nothingness is difficult to define scientifically. When we speak of nothing in everyday life, we often mean an absence of things we can see or touch, an empty room, a quiet space. But in the realm of cosmology, and particularly when contemplating the moments before the Big Bang, this seemingly simple idea of nothingness becomes profoundly complex. Scientists grapple with what nothing truly means in a physical context. Is it simply the absence of matter and energy? Or does it extend to the absence of space, of time, of physical laws themselves? Consider the quantum vacuum. In quantum field theory, even what we might perceive as empty space is a dynamic, seething sea of virtual particles constantly popping in and out of existence. These fleeting entities, though appearing and disappearing in fractions of a second, carry energy and influence. So, even in the absence of stuff, as we conventionally understand it, there is still a fundamental energetic substratum. This suggests that a true, absolute void, devoid of all potential and all activity, may not be a physically attainable state. Furthermore, if we consider the possibility of a pre-Big Bang universe, or a state that preceded it, we must also question the existence of space and time. Our current understanding of physics is deeply intertwined with the fabric of spacetime. If spacetime itself did not exist in the way we understand it, then concepts like absence or void lose their familiar meaning. How can something be absent from a place if there is no place? How can something not exist over a duration if there is no duration? The singularity at the heart of the Big Bang, while often described as an infinitely dense point, also represents a breakdown in our current physical models. It's a point where our equations cease to provide meaningful answers, a boundary beyond which our scientific intuition struggles to venture. This suggests that our conventional tools for defining existence and non-existence may not be sufficient for describing the ultimate origins. The very act of observation, of measurement, implies the existence of something to be observed and measured. To define nothingness scientifically, we would ideally need a framework that exists independently of any physical reality, a metaphysical stage upon which the absence of physical phenomena could be noted. But such a framework is elusive, perhaps even contradictory to the scientific endeavor, which is inherently about understanding the physical universe. Therefore, when cosmologists ponder the before, they are not necessarily envisioning a vast, empty expanse. They are contemplating a state where our familiar concepts of space, time, matter, and energy may have been fundamentally different, or perhaps entirely absent, replaced by something far more abstract and elusive. The scientific definition of nothingness before the Big Bang is not a simple void, but rather a profound question mark, a frontier of our current understanding, pushing the boundaries of what we can conceive and measure. It is a space of potential, a realm of possibility that our language and our current physics struggle to encompass. The silence before the cosmic dawn whispers not of emptiness, but of a mystery yet to be fully unfurled. Black holes could be gateways to other universes or previous eras. The enigmatic nature of black holes has long captivated the human imagination, and among their many mysteries lies the tantalizing possibility that they are not merely cosmic dead ends, but rather conduits to realms beyond our current comprehension. While our direct observation of the interior of a black hole is, by definition, impossible due to the event horizon, theoretical physics offers several compelling avenues for exploring this profound idea. One prominent theoretical framework that hints at such possibilities is the concept of wormholes, also known as Einstein-Rosen bridges. These hypothetical tunnels through spacetime could, in theory, connect disparate points in our own universe, or even link our universe to entirely different ones. The extreme gravitational forces at play within a black hole's structure, particularly near its singularity, are theorized to warp spacetime so severely that such a bridge could potentially form. However, the stability and traversability of such wormholes remain highly speculative, with many physicists suggesting that they would likely collapse too quickly to allow passage, or that exotic matter with negative energy density would be required to keep them open, matter for which we have no definitive observational evidence. Another related theoretical concept stems from the study of quantum gravity, a field that seeks to unify Einstein's theory of general relativity with quantum mechanics. In some models of quantum gravity, the singularity at the heart of a black hole is not an infinitely dense point, but rather a region where quantum effects become dominant. These effects could, in principle, lead to a bounce or a transition to a different state, potentially allowing matter and information to emerge elsewhere. This is where the idea of black holes as gateways to previous eras gains traction. Imagine a universe that undergoes a cyclical process of expansion and contraction, with black holes acting as mechanisms to transfer matter and energy from one cycle to the next. In this scenario, what appears to us as the absolute end of matter and light falling into a black hole could, in reality, be a transformation and re-emergence in a nascent, younger universe. This is reminiscent of certain Big Bounce cosmological models, where the universe collapses and then rebounds, creating a new period of expansion. Furthermore, the information paradox associated with black holes, the question of whether information is truly lost when it falls into a black hole, or if it is somehow preserved, also fuels these speculative ideas. If information is not lost, then it must go somewhere. Some theories propose that this information could be encoded on the event horizon, or that it could be carried through to another universe or a subsequent cosmic epoch. The very act of a black hole evaporating through Hawking radiation, a process by which black holes are thought to slowly lose mass over immense timescales, might itself be a form of information leakage, albeit in a highly scrambled and energetic form. While these concepts are currently on the frontiers of theoretical physics and are far from being empirically verified, they offer a profound reframing of black holes, moving them from the realm of ultimate destruction to potential portals of cosmic continuity and rebirth. They remind us that our current understanding of the universe is a snapshot, and that the universe may hold secrets far more intricate and interconnected than we can currently grasp. Within the crushing embrace of a black hole, perhaps lies not an end, but a gentle whisper of beginnings yet to unfold across the vast tapestry of existence. The idea of a bounce challenges the notion of a singular start. Imagine, if you will, a universe that doesn't simply begin with a bang, but rather with a cosmic rebound. This is the elegant concept of the Big Bounce, a theoretical framework that offers a compelling alternative to the singularity predicted by classical Big Bang cosmology. Instead of an infinitely dense, infinitely hot point from which everything emerged, The Big Bounce proposes that our universe originated from the collapse of a previous universe. In this model, the universe undergoes a cycle of expansion and contraction, a grand cosmic breath, inhaling and exhaling across unimaginable timescales. When a universe reaches its maximum expansion, its constituent matter and energy begin to contract under the relentless pull of gravity. This contraction continues, compressing the universe, but instead of reaching a true singularity, a point of infinite density where our current laws of physics break down, it reaches a point of maximum density and then, crucially, bounces back. This bounce is not a sudden, violent explosion in the traditional sense, but a transition, a phase change in the fabric of space-time. What triggers this bounce? This is where the frontiers of theoretical physics become truly fascinating. Theories like loop quantum cosmology suggest that at extremely high densities, quantum gravitational effects become dominant. These effects, governed by the quantized nature of spacetime itself, create a repulsive force that counteracts the gravitational collapse, preventing a singularity and initiating the expansion phase. Think of it like a spring being compressed to its absolute limit, and then, instead of snapping, it gracefully springs back. In this cyclical scenario, the Big Bang as we understand it is not the absolute beginning, but rather the beginning of our current cycle of expansion. The universe would have existed before, in a contracting phase, and the Big Bang marks the point where that contraction turned back into expansion. This perspective fundamentally alters our understanding of cosmic origins. It implies that the universe is eternal, not in a static sense, but in a dynamic, perpetually renewing one. It opens up the possibility that the conditions we observe today, the distribution of matter, the fundamental constants of nature, could be influenced by the remnants or properties of a prior cosmic era. The very emptiness of space, the vacuum, is understood not as a void, but as a dynamic medium capable of supporting these immense transformations. This cyclic model also addresses some of the conceptual difficulties associated with a singular beginning. For instance, where did the initial stuff come from if there was absolutely nothing before? The Big Bounce elegantly sidesteps this by suggesting that the stuff was already there, part of a prior universe. It also offers potential solutions to puzzles like the flatness problem and the horizon problem, which are often addressed by cosmic inflation. In some bounce models, the very process of contraction and subsequent bounce can naturally lead to a universe that is both flat and homogeneous on large scales. The implications are profound. It means that the universe we inhabit is not an isolated event, but part of an ongoing, perhaps infinite, cosmic drama. Each expansion is a new chapter, born from the ashes of the previous one. The start, we perceive, is merely a transition, a moment of profound cosmic metamorphosis. The idea of a cosmic bounce suggests that our universe is a breath inhaled from the exhale of a universe that came before. Our observable universe might be a bubble within a larger structure. Imagine, if you will, a vast expanse, far grander than anything we can currently perceive. Within this immense, perhaps eternal cosmic ocean, our entire universe, with all its galaxies, stars, and planets, might exist as a singular, expanding bubble. This is the intriguing concept explored by theories such as eternal inflation. In this framework, the process of inflation, the rapid expansion that is thought to have occurred in the moments after the Big Bang, doesn't just happen once and then cease. Instead, it's proposed that inflation continues indefinitely in some regions of this larger metastructure. Think of it like a perpetually boiling pot of water, where new bubbles are constantly forming, expanding, and detaching from the main body of the water. Each of these bubbles in this analogy could be an entirely separate universe, with its own unique set of physical laws, constants, and even dimensions. Our own universe, then, would be just one such bubble that pinched off from the inflating background, continuing its own expansion. This idea offers a potential explanation for why our universe seems so finely tuned for life. If there are countless other universes, each with different properties, it's not surprising that we find ourselves in one that supports our existence. It's a form of anthropic principle. We observe the universe to be the way it is because if it were any different, we wouldn't be here to observe it. The larger structure in which our bubble resides could be infinitely vast, and the process of bubble formation might be ongoing, creating an endless cosmic foam. The interactions between these bubbles, if any, are currently beyond our observational reach. We are, in essence, confined to our own cosmic neighborhood, our observable universe, and the true extent of reality, if it includes this multiverse, remains a profound mystery. This perspective shifts our understanding of our place in existence, suggesting that our cosmic home is not unique, but perhaps one of an innumerable collection, each born from the same fundamental inflating fabric. It's a humbling, yet awe-inspiring thought, that the very space and time we inhabit might be a transient formation within a grander, more complex cosmic tapestry, a testament to the boundless creativity of the universe's underlying principles. This concept also touches upon the very nature of probability and existence. If the possibilities are truly infinite, then perhaps all conceivable universes do, in fact, exist somewhere within this grander framework. The question then becomes not whether such universes can exist, but how we might, in principle, ever detect or comprehend them. For now, they remain theoretical constructs, born from our deepest explorations into the fundamental nature of reality, offering a glimpse into a cosmos far richer and more diverse than we might have ever imagined. The implications are staggering, suggesting that the Big Bang was not an absolute beginning, but rather a local event, a singular birth within an eternal, ever-expanding cosmic genesis. Our observable universe, a sphere of light and matter reaching out to the farthest corners of our perception, may indeed be just one small, luminous droplet in an infinite cosmic ocean. And in the quiet expansion of our own bubble, we find a perspective that stretches beyond our immediate horizon, a gentle reminder that even the grandest of our cosmic homes can be a part of something even more magnificent. The ultimate fate of the universe could inform its origin. Consider for a moment the grand narrative of existence, the cosmic saga that unfolds across billions of years. We often focus, quite naturally, on the beginning, that enigmatic moment of the Big Bang, the genesis of space and time as we understand them. But science, in its relentless pursuit of understanding, suggests that the end, the ultimate destiny of our universe, might hold profound clues about its very inception. This is not a simple matter of cause and effect in the linear sense we experience daily, but rather a deep, interconnected truth about the fundamental nature of reality. If our universe is destined to expand forever, cooling and thinning into a cold, dark expanse, a state often termed the heat death, or Big Freeze, this trajectory might imply certain initial conditions. For instance, a universe born with precisely the right amount of energy and matter to sustain such an unending expansion would require a very specific set of parameters at its birth. The absence of a cosmic rebound, or a subsequent collapse into another singularity, could point towards an origin that was inherently geared towards this perpetual outward motion. The flatness of our universe, for example, a geometrical property observed through cosmic microwave background radiation, is a crucial piece of evidence supporting ongoing expansion, and might be a direct consequence of inflationary processes that occurred fractions of a second after the Big Bang. itself possibly influenced by a pre-existing state. Conversely, if theoretical models that predict a big crunch, where the universe eventually stops expanding and begins to contract, were to be accurate, this would fundamentally alter our understanding of its origin. A universe destined for collapse might have begun in a fundamentally different state, perhaps with a higher initial density or a different composition of dark energy, the mysterious force driving expansion. Such a scenario could even lend credence to cyclic models, where a big crunch leads to a subsequent Big Bang, suggesting a continuous, eternal process of cosmic birth and rebirth. In these cyclic scenarios, the origin is not a singular event but a transition, a transformation from the end of one universe to the beginning of another. Furthermore, the very nature of fundamental constants, the values of physical laws like the speed of light, the gravitational constant, or the charge of an electron, is a subject of intense debate. If these constants are discovered to be inherently linked to the universe's ultimate fate, then understanding that fate becomes paramount to understanding why these constants have the values they do, and by extension, why the universe began the way it did. For example, some theories propose that the strength of fundamental forces might evolve over cosmic timescales. If the universe is heading towards a state where certain forces become dominant or fade away, it suggests that these forces might have been in a different balance at its inception. The concept of entropy, the measure of disorder in a system, also plays a critical role. The second law of thermodynamics dictates that entropy always increases in a closed system. If the universe is heading towards maximum entropy, a state of ultimate disorder, this increasing trend must have started from a state of very low entropy at the Big Bang. This low entropy beginning is a profound puzzle, and understanding the universe's ultimate state of maximal entropy helps us to better define and appreciate that initial, almost impossibly ordered starting point. The ongoing quest to detect gravitational waves from the very earliest moments of the universe, or to probe the nature of dark energy and its potential evolution, are all avenues that connect the universe's end to its beginning. By studying the cosmic echoes of its final moments, we gain a deeper, more nuanced perspective on the conditions that must have prevailed at its genesis. It's as if the universe, in its vastness, whispers secrets of its birth through the language of its eventual demise, reminding us that all things, from the smallest particle to the grandest cosmic structure, are part of an unbroken, magnificent continuum. The universe's final breath may well reveal the first gasp of its existence. The quest for a theory of everything might unlock pre-Big Bang secrets. Imagine, if you will, a grand tapestry woven with the threads of all known physical laws. We have one set of rules that govern the incredibly small, the realm of quantum mechanics, describing the bizarre and probabilistic dance of particles. Then we have another, equally elegant set of rules, Einstein's theory of general relativity, which masterfully describes the immense, the cosmic ballet of gravity, space-time, and celestial bodies. For decades, physicists have striven to reconcile these two seemingly disparate descriptions of reality into a single, unified framework, a theory of everything, or TOE. This isn't merely an academic exercise. It's a profound yearning to understand the fundamental nature of existence itself. Such a theory would, in principle, be able to explain every fundamental force and every fundamental particle in the universe, from the smallest subatomic tremor to the grandest galactic sweep. Why is this relevant to our question of what came before the Big Bang? Because the very moment of the Big Bang, the initial flash of creation, is precisely where these two pillars of modern physics, quantum mechanics and general relativity, notoriously clash. At the unimaginably high densities and energies of the singularity, the equations of general relativity break down, yielding infinities that signal our current understanding is incomplete. Similarly, quantum effects, which dominate the microworld, must have played a crucial role in the universe's nascent moments, yet we lack a quantum description of gravity to fully grasp this. A successful TOE would provide the missing mathematical language, the bridge between the quantum and the cosmic, allowing us to describe these extreme conditions. Theories like string theory and loop quantum gravity are current contenders, each offering a different perspective on how gravity might be quantized, and how the very fabric of spacetime might behave at its most fundamental level. If these theories, or a future iteration of them, can successfully unify all forces and particles, they might also offer predictions or frameworks that extend our understanding backward in time, beyond the point where our current cosmological models become inscrutable. They might reveal that the singularity was not an absolute beginning, but rather a transition point, a bounce from a previous cosmic phase, or a phase transition within a larger, pre-existing structure. By understanding the fundamental building blocks and forces of the universe at their deepest level, we might finally gain the perspective needed to peer into the cosmic dawn, and perhaps even before it. In the grand unified dream of physics, the echoes of what was may whisper through the very fabric of what is, guiding us toward the stillness before the first light. The vacuum energy could be the source of cosmic creation. Imagine for a moment the concept of a vacuum, not an empty space, but rather a dynamic, energetic field teeming with potential. This is the essence of vacuum energy, a fundamental concept in quantum field theory that suggests that even in the apparent emptiness of space, there exists a pervasive, intrinsic energy. This energy is not static. It's a vibrant, fluctuating sea of virtual particles constantly popping into and out of existence. These are not particles in the conventional sense, but rather fleeting excitations of quantum fields. They appear, exist for an infinitesimally brief moment, and then vanish, their existence governed by the Heisenberg uncertainty principle, which allows for temporary violations of energy conservation. This constant, subtle churning of the vacuum is far from being a mere theoretical curiosity. It has measurable consequences. For instance, the Casimir effect, a phenomenon where two uncharged, parallel conducting plates placed very close together in a vacuum experience an attractive force, is a direct manifestation of vacuum energy. The presence of the plates subtly alters the distribution of virtual particles in the vacuum between them compared to the region outside, leading to a pressure difference that pushes the plates together. This is a tangible, experimental verification that the vacuum is indeed a place of energetic activity. Now, let's consider how this energetic vacuum might relate to the origin of the universe. One of the leading ideas is that the Big Bang itself was not an explosion in pre-existing space, but rather the rapid expansion of space itself, driven by an enormous release of vacuum energy. During a period known as cosmic inflation, the universe is theorized to have undergone an exponential expansion, growing from an unimaginably small size to something much larger in a fraction of a second. This period of inflation is thought to be powered by a form of vacuum energy, often referred to as the inflaton field. As this field decayed, its energy was converted into the matter and radiation that we observe today, effectively creating the universe from this primal energy source. It's as if the vacuum, in its inherent energetic nature, possessed the potential for everything that followed. This idea offers a compelling explanation for the homogeneity and flatness of the observable universe, as inflation would have smoothed out initial irregularities and stretched the fabric of spacetime to be nearly flat. The vacuum energy, therefore, is not just a passive background. It's an active participant in the cosmic story. It's a reservoir of potential, a hidden engine that, under the right conditions, could have triggered the grand unfolding of existence. The very fabric of spacetime, it seems, is imbued with an energy that could have been the ultimate genesis. This profound concept challenges our intuitive notions of creation, suggesting that the origin of everything might have sprung from the energetic hum of what we perceive as nothingness. From the energetic hum of emptiness, all existence may have first bloomed. The universe's expansion rate might hold clues to its past. The astonishing fact that our universe is not static but perpetually expanding is a cornerstone of modern cosmology. But this expansion is not a simple, uniform outward push. Its rate, and how it has changed over cosmic history, is a deeply revealing story. Imagine a vast, invisible tide carrying galaxies further apart from one another. For a long time, astronomers assumed this expansion would gradually slow down due to the gravitational pull of all the matter within the universe. It was a natural, intuitive thought, much like a ball thrown upwards eventually slowing its ascent before falling back. However, observations in the late 1990s, particularly those studying distant supernovae, the explosive deaths of massive stars, revealed something utterly unexpected. These cosmic lighthouses, when observed from vast distances, appeared fainter than they should have been if the expansion had been slowing. This implied that the expansion was not only continuing, but actually accelerating. This acceleration is one of the most profound mysteries in physics, attributed to a mysterious force known as dark energy. Dark energy, which seems to permeate all of space, acts as a sort of anti-gravity, pushing spacetime itself apart at an ever-increasing pace. The precise nature and density of this dark energy, and how it has evolved over billions of years, are critical pieces of the puzzle. By meticulously measuring the expansion rate at different epochs of the universe's history, from the very early moments after the Big Bang, through the period when matter dominated, to the current era of dark energy dominance, scientists can essentially rewind the cosmic clock. The subtle variations in this expansion rate, the moments when it may have slowed or sped up, are like fingerprints left by the universe's earliest moments and the fundamental forces that shaped it. These measurements help us constrain theoretical models, testing predictions about the energy content of the universe and the very fabric of spacetime. If the expansion rate was different in the past, it could point to variations in the fundamental constants of nature, or perhaps even to the existence of exotic forms of matter or energy that have long since faded away. Understanding the history of cosmic expansion allows us to build more accurate models of how the universe evolved from its initial hot, dense state to the vast, intricate cosmos we observe today. It's a continuous process of refinement, where each new observation of the expansion rate brings us closer to understanding the universe's grand narrative, and in doing so, potentially sheds light on what existed, or how things were, before the cosmic dawn. The rate of expansion is not just a number. It's a dynamic indicator of the universe's fundamental character and its journey through time, a journey that might have begun in ways we are only just beginning to comprehend. The accelerating dance of cosmic expansion whispers tales of forces and beginnings, guiding our gaze back through the veils of time. The cosmic microwave background radiation is a faint echo of origins. Imagine, if you will, a moment so profoundly ancient that our very concept of time begins to fray at the edges. A time when the universe, though perhaps not in the vast, structured form we perceive today, was in a state of intense, energetic unity. This is the era from which our topic, the cosmic microwave background radiation, or CMB, draws its astonishing narrative. It is, in essence, the oldest light in the universe, a whisper from the cosmic dawn, a relic of a time when the cosmos was a mere fraction of its current age and vastly different in its composition and behavior. To understand the CMB, we must journey back to a period approximately 380,000 years after the Big Bang. Before this epoch, the universe was a scorching, opaque plasma. Photons, the fundamental particles of light, were constantly scattering off free electrons and protons, much like light struggling to penetrate a thick fog. The universe was essentially a luminous soup, too dense and energetic for light to travel freely. It was a closed, interconnected system, where every photon was engaged in a perpetual dance of collision. Then a remarkable transformation occurred. As the universe continued to expand and cool, it reached a critical temperature. At this point, the energy of the photons dropped sufficiently for electrons to bind with protons, forming stable atoms of hydrogen and helium. This process, known as recombination or decoupling, was a pivotal moment. Suddenly, the universe became transparent. The photons, freed from their constant scattering, were able to travel unimpeded through space. These are the very photons that, after billions of years of journeying across the cosmos, we can now detect as the cosmic microwave background radiation. The CMB is not a uniform glow. It is a remarkably uniform field of radiation filling all of space, but with minute temperature fluctuations, variations measured in mere microkelvins. These tiny ripples, initially imperceptible, are of immense scientific importance. They represent the seeds of cosmic structure. Where the temperature was slightly cooler, there was slightly more matter, and gravity, over eons, began to pull this matter together, eventually forming the galaxies, stars, and planets that populate our universe today. The CMB, therefore, is not just a snapshot of the early universe. It is a blueprint, a cosmic fingerprint revealing the initial conditions that led to everything we see. The discovery of the CMB in 1964 by Arno Penzias and Robert Wilson was a monumental event, providing powerful evidence for the Big Bang theory. It was a serendipitous discovery, initially mistaken for an annoying background noise in their radio antenna. But as they investigated, they realized they had stumbled upon something far more profound, the afterglow of creation itself. This faint microwave radiation, emanating from every direction in the sky, is a constant reminder of our universe's fiery birth and its subsequent evolution. The study of the CMB continues to be a cornerstone of modern cosmology. Missions like COBE, WMAP, and Planck have mapped these temperature fluctuations with ever-increasing precision, allowing scientists to refine our understanding of the universe's age, composition, and expansion rate. The patterns within these fluctuations provide insights into the fundamental physics that govern the universe in its infancy, including the nature of dark matter and dark energy, and even hints about the possibility of inflation, a period of rapid expansion immediately after the Big Bang. The cosmic microwave background radiation, then, is more than just a scientific observation. It is a profound connection to our cosmic heritage. It is the universe speaking to us across unimaginable distances of space and time, sharing its earliest memories. It's a gentle reminder that the vastness we perceive is built upon a foundation of incredible simplicity and energetic beginnings. And so, this ancient light, this faint echo of origins, bathes us in its gentle embrace, a subtle testament to the grand, unfolding story of existence. The search for gravitational waves from the very early universe continues. Imagine, for a moment, a symphony so profound, so ancient, that its echoes are only just beginning to reach us. This is the realm of gravitational waves, ripples in the very fabric of spacetime, born from the most cataclysmic events imaginable. While we have successfully detected gravitational waves from the mergers of black holes and neutron stars in our relatively recent cosmic past, the ultimate prize, the signal from the universe's infancy, remains an elusive whisper. The Big Bang itself, or more accurately, the inflationary epoch that followed, is theorized to have generated a unique and powerful background of gravitational waves. These primordial waves, unlike those from stellar collisions, would have been imprinted on spacetime during a period of unimaginably rapid expansion, just fractions of a second after the initial event. Detecting these ancient tremors would be akin to finding the very first notes of the cosmic symphony, offering direct evidence of the physics that governed the universe when it was smaller than an atom. Current and future observatories, both ground-based and spaceborne, are being designed with unprecedented sensitivity to sift through the cosmic noise and isolate this faint, primordial hum. Missions like LISA, Laser Interferometer Space Antenna, are specifically engineered to detect these very low-frequency gravitational waves, which would have been stretched by the universe's expansion over billions of years. The challenge is immense, as these signals are incredibly weak, easily masked by other astrophysical phenomena and instrumental noise. Yet, the scientific drive to understand our deepest origins propels this ongoing quest. The potential discoveries are staggering: confirmation of inflationary theory, insights into the fundamental forces at play during the universe's birth, and perhaps even glimpses into physics beyond our current standard model. It's a testament to human curiosity and ingenuity, a patient listening for the universe's first breath. This search is not merely about detecting a signal. It is about reconstructing our own genesis, about understanding the fundamental conditions that allowed for the very existence of stars, galaxies, and ultimately ourselves. The scientific endeavor, in its most profound sense, is a journey back to the beginning, a meticulous unraveling of the cosmic tapestry, thread by ancient thread. The faint, persistent hum of possibility resonates through the cosmos, beckoning us to listen closer, to refine our senses, and to continue this profound exploration. In the silent hum of the universe, we listen for the first, faint tremors of creation, a lullaby whispered from the dawn of time. The fine-tuning of universal constants suggests a deeper context. Consider for a moment the remarkable precision with which the fundamental constants of our universe are set. These aren't just arbitrary numbers. They are the bedrock upon which all of existence, as we perceive it, is built. Think of gravity, for instance, described by Newton's law of universal gravitation, which itself relies on the gravitational constant. If this constant were even slightly different, the universe would be a vastly different place. If gravity were stronger, stars would burn out too quickly, leaving no time for complex chemistry to evolve, let alone life. If gravity were weaker, stars and galaxies might not have formed at all, and the universe would be a diffuse, cold expanse of hydrogen and helium. Then there's the electromagnetic force, governed by the elementary charge and the speed of light. The precise balance between the strong nuclear force, the weak nuclear force, and electromagnetism dictates the stability of atomic nuclei. If the strong nuclear force were only a few percent weaker, deuterium, a crucial element for the formation of heavier elements in stars, would not be stable. If it were slightly stronger, all the hydrogen in the universe would have fused into helium shortly after the Big Bang, leaving no fuel for stars and no complex chemistry. The masses of fundamental particles, like the electron and the proton, are also exquisitely balanced. The ratio of their masses is around 1836:1. If this ratio were significantly different, the chemical bonds that hold molecules together, the very basis of life, would be impossible. The cosmological constant, which drives the accelerated expansion of the universe, is another example. Its observed value is incredibly small, almost vanishingly so, compared to what theoretical physics might predict. If it were even slightly larger, the universe would have expanded so rapidly after the Big Bang that matter would never have coalesced into stars and galaxies. If it were significantly smaller, the universe might have already collapsed back on itself. This phenomenon, often referred to as the fine-tuning problem, is deeply perplexing. It's as if the universe was deliberately set up with these specific values to allow for the emergence of complexity, stars, planets, and ultimately, consciousness. While some scientists seek explanations within the framework of existing physics, such as the idea of a multiverse where countless universes exist with varying constants, and we simply happen to inhabit one that is life-permitting, others see this as a profound indicator of something more. It suggests that the very fabric of reality, the underlying principles that govern existence, might be imbued with a purpose or a context that transcends our current scientific grasp. This exquisite calibration hints at a design, a profound intentionality woven into the cosmic tapestry, inviting us to ponder the very nature of our being and the universe we inhabit. And so, the delicate balance of cosmic dials whispers of a grander design, a symphony of numbers that orchestrates our very existence. Philosophical perspectives on causality and existence are relevant. When we venture into the profound question of what existed before the Big Bang, we inevitably find ourselves stepping onto the hallowed ground of philosophy. Science, with its rigorous methods and observational data, can only take us so far. At the very edge of our current understanding, where time itself may have begun its measured march, the nature of existence and the very concept of cause and effect become subjects of deep contemplation. For millennia, philosophers have grappled with the fundamental questions. Why is there something rather than nothing? What does it mean to exist? And how do we understand the relationship between events, particularly when the very framework of time, as we perceive it, might not have been in place? Consider the principle of causality. We are accustomed to thinking that every effect must have a cause, and that this cause must precede the effect in time. This is the bedrock of our everyday experience and a cornerstone of scientific inquiry. If we ask, what caused the Big Bang? We are implicitly assuming a temporal order, a before and an after. However, if the Big Bang was, as some theories suggest, the origin of spacetime itself, then applying our linear understanding of causality becomes problematic, perhaps even meaningless. Could it be that the very notion of cause requires time to exist? If so, then the question of what caused the Big Bang might be a category error, like asking what is north of the North Pole. This leads us to the philosophical concept of existence. What does it mean for something to be? Does existence require a temporal dimension? Can something exist outside of time? Some philosophical traditions have explored ideas of an eternal, timeless realm, a substratum from which the temporal universe emerges. Thinkers like Plato, with his theory of forms, suggested a realm of perfect, unchanging essences that exist independently of the physical, temporal world. While not a direct scientific model for pre-Big Bang physics, these philosophical explorations offer a different lens through which to view the origin of reality, suggesting that what we perceive as existence might be a specific manifestation or a phase within a larger, perhaps timeless, reality. Furthermore, the very act of questioning the origin of the universe is an expression of our innate human drive to find meaning and order, a fundamentally philosophical pursuit. We seek to understand our place within the grand tapestry of existence, and our origins are intrinsically linked to that quest. The aha, moments we experience in science often have a philosophical resonance, prompting us to reconsider our deepest assumptions about reality. For instance, the idea that the universe might have emerged from a state of quantum vacuum, a concept rooted in physics, also touches upon philosophical debates about potentiality and actuality. Is a state of pure potentiality truly nothing? Or is it a form of existence in itself, a fertile ground from which all possibilities can arise? When we consider the possibility of a multiverse, the philosophical implications become even more expansive. If our universe is just one among an infinite or vast number of others, each with its own unique properties and perhaps even its own set of physical laws, then our existence within this particular universe might be a matter of chance, a specific outcome from an immense cosmic lottery. This can lead to profound reflections on contingency and necessity, on whether our universe's existence is a fundamental necessity or a contingent event. The philosophical concept of brute facts, facts that simply are, without further explanation, might also come into play when contemplating the ultimate origin of reality. The philosophical exploration of nothingness itself is a fascinating rabbit hole. Is it the absence of everything, including space, time, and physical laws? Or is it a state of pure, unmanifested potential? Some physicists, when discussing the quantum vacuum, hint at the latter, a state brimming with virtual particles and energy fluctuations, far from the absolute void we might intuitively imagine. This philosophical nuance is crucial because it bridges the gap between our intuitive understanding and the more abstract scientific models. It allows us to approach these cosmic mysteries with an open mind, recognizing that our everyday concepts might not be sufficient to grasp the true nature of ultimate origins. Ultimately, the philosophical perspectives on causality and existence are not mere academic curiosities. They are essential tools for framing our inquiries, for interpreting the scientific evidence, and for finding a sense of peace and perspective as we ponder the unfathomable beginnings of everything. These deep inquiries into causality and existence whisper to us that our temporal journey is but one facet of a grander, perhaps timeless, reality, reminding us that wonder can be found even in the most profound unknowns. The concept of eternity challenges linear temporal thinking. Our human experience is deeply rooted in the progression of time, a relentless march from past to present to future. We mark our lives by seconds, minutes, days, and years, each a discrete segment in a seemingly endless line. This linear perspective is fundamental to our understanding of cause and effect, of growth and decay, of beginnings and endings. It is the framework within which we build our narratives, make our plans, and grapple with our mortality. However, when we turn our gaze towards the vastness of the cosmos, or delve into the most fundamental questions of existence, this linear model begins to feel incomplete. The idea of eternity in its most profound sense is not simply an unimaginably long duration of time. It is a state that transcends time altogether. It is a concept that our minds, wired for sequential experience, struggle to fully grasp. Think of it not as an infinite line, but perhaps as a boundless ocean, or an infinite, unmoving expanse. In such a realm, the distinctions between past, present, and future dissolve. Everything simply is. This is where the challenge to our linear thinking becomes most apparent. If we consider the very early universe before the Big Bang, the very notion of before becomes problematic. If time itself began with the Big Bang, then asking what happened before is akin to asking what lies north of the North Pole. The question, framed within our temporal understanding, becomes nonsensical. Eternity, in this context, suggests a state or a reality that exists outside of this beginning and end framework. Consider philosophical perspectives that have grappled with this for millennia. Many spiritual traditions speak of an eternal realm, a divine presence that is always and everywhere, unconstrained by the passage of moments. While these are not scientific explanations in the empirical sense, they reflect a deep human intuition that there might be something more, something that exists beyond the ticking clock. Scientifically, the concept of eternity can be explored through theoretical frameworks that push the boundaries of our current understanding. For instance, some cosmological models, like those involving a cyclical universe, suggest a series of expansions and contractions, an endless dance of creation and destruction. While each cycle might have its own temporal progression, the overall process could be viewed as eternal, a continuous unfolding without a definitive ultimate beginning or end. Another avenue is the realm of quantum physics. At the Planck scale, the smallest measurable units of space and time, our classical notions of continuity and linearity break down. Some theories suggest that time itself might emerge from a more fundamental, timeless reality. In such a timeless substrate, events that appear sequential to us might exist simultaneously, or in a state of potentiality that is beyond our temporal comprehension. The very idea of a universe that has always existed, or that will exist forever, forces us to confront the limitations of our temporal perception. We are creatures of duration, of change, of becoming. Eternity, on the other hand, points towards a state of being, a timeless permanence that is both awe-inspiring and deeply humbling. It reminds us that our experience of time, while vital for navigating our world, might be a localized phenomenon, a specific mode of perception within a potentially far grander, timeless reality. The contemplation of eternity invites us to step outside the confines of our personal timelines and consider a perspective where all moments, all possibilities might coexist. It is a thought experiment that can loosen the grip of our anxieties about the past and our fears about the future, by hinting at a reality that is fundamentally different from the one we experience day to day. It suggests that perhaps, in a way we cannot fully articulate, everything is already and forever complete. Eternity, then, is not a destination in time, but a horizon that redefines the very landscape of existence. And in this quiet contemplation of timelessness, the urgent grip of linear moments begins to gently loosen. Our current understanding is a work in progress, a beautiful mystery. The tapestry of the cosmos, woven with the threads of time and space, is an endlessly unfolding narrative. As we peer back towards the genesis of our universe, towards that enigmatic moment we call the Big Bang, we find ourselves not at a definitive endpoint of knowledge, but at the very edge of our present comprehension. The questions that arise are profound, touching upon the very essence of existence, and the answers, when they come, are often more wondrous and complex than we could have initially imagined. Our journey to understand what came before the Big Bang is not a linear march towards absolute certainty, but a continuous dance with the unknown, a perpetual refinement of our models and theories. Consider the immense scale of cosmic history, billions of years compressed into a single, almost incomprehensible event. The Big Bang, as we currently understand it, describes the rapid expansion of space-time from an extremely hot, dense state. It's a powerful framework, supported by a wealth of observational evidence like the cosmic microwave background radiation and the abundance of light elements. Yet, this framework has its limits. It doesn't fully explain what initiated that expansion, or what, if anything, existed in the moments preceding it. The singularity, a point of infinite density and temperature, is less a description of a physical reality and more a signal that our current laws of physics break down under such extreme conditions. This is where the work-in-progress aspect of science truly shines. Instead of a static set of facts, we have a dynamic, evolving understanding. Theories like loop quantum cosmology propose a bounce rather than a singularity, suggesting that a previous universe may have collapsed and then rebounded into our current expansion. String theory, with its extra dimensions and fundamental vibrating strings, offers a different lens, hinting at a pre-existing quantum foam from which our universe could have emerged. These are not just abstract mathematical constructs. They are attempts to push the boundaries of what we can conceive, to build conceptual bridges across the chasm of our ignorance. The very concept of before becomes problematic when we consider that time itself may have originated with the Big Bang. If time is a dimension that began its journey at that initial moment, then asking what existed before is akin to asking what lies north of the North Pole. The question itself might be ill-posed within our current framework. This challenges our intuitive, linear perception of causality and existence, prompting us to consider entirely new paradigms. Perhaps the universe is not a single, isolated event, but part of a grander, cyclical process, or perhaps it is one bubble among an infinite sea of other universes, each with its own origin story. The beauty of this mystery lies in its invitation to wonder. It reminds us that our knowledge, while impressive, is still nascent. We are like children learning to read the grand cosmic book, deciphering letters and words, slowly piecing together sentences, but still far from grasping the full narrative. The pursuit of understanding what preceded the Big Bang is not just an academic exercise. It's a philosophical quest that deepens our appreciation for the universe and our place within it. It fosters humility, acknowledging the vastness of what we don't yet know, and ignites a spark of curiosity that drives scientific exploration forward. This ongoing investigation, this continuous refinement of our models, this willingness to embrace the profound questions that have no easy answers, this is the essence of scientific progress. It is a testament to human ingenuity and our insatiable desire to comprehend the cosmos. The universe, in its enigmatic origins, offers us a profound lesson that the greatest discoveries often lie at the frontier of our current understanding, in the quiet spaces where imagination and evidence converge, creating a beautiful, ever-expanding mystery. And in this vast, unfolding mystery, there is a profound peace to be found. The universe's journey from its unknown beginnings to its grand expanse is a story of creation, transformation, and endless possibility. You are a part of this story, a conscious observer in this grand cosmic ballet. The questions about what came before the Big Bang are not meant to stress you, but to invite you into a deeper contemplation of existence, to gently expand your perspective and allow you to rest in the quiet wonder of it all. Sleep well. Our calm exploration has covered the profound and often mind-bending question of what might have existed before the Big Bang. We've gently touched upon the idea that our universe, vast and magnificent as it is, may not be the sole beginning, but perhaps a chapter in an infinitely grander narrative. We've considered the intriguing possibilities of quantum fluctuations, cyclic universes, and the fundamental nature of time itself, realizing that our current scientific understanding, while ever expanding, still encounters the edges of the truly unknown. Tonight, we have reviewed the principles of scientific inquiry that push the boundaries of our perception, daring to ask questions that challenge our most fundamental assumptions about existence. We've seen how concepts like the multiverse, string theory, and loop quantum cosmology offer tantalizing glimpses into potential realities preceding our own cosmic dawn. Each of these ideas, while complex, serves to remind us of the sheer wonder inherent in the universe and the persistent human drive to understand our place within its grand tapestry. As we reflect on these vast cosmic scales and the potential for universes to emerge, expand, and perhaps even recede, it is natural to feel a sense of profound perspective. The anxieties and stresses of our daily lives, when viewed against the backdrop of cosmic eternity and the unfathomable origins of reality, can begin to soften, to seem less overwhelming. You are a part of this immense, unfolding story, a fleeting but precious expression of the universe's ongoing creation. Allow this understanding to wash over you, a gentle tide of cosmic significance, bringing with it a deep sense of peace. It is time to rest now. Your mind has been gently stimulated, your curiosity soothed. You have explored the edges of the cosmos from the safety and comfort of your own space. Let the quiet wonder of these ideas lull you into a state of deep relaxation. Sleep well. Good night. It is time to rest now. If you happen to still be awake, you can drift into the next chapter now, allowing the gentle exploration to continue, or simply allow the stillness to embrace you.